In the previous videos, we've learned how to consolidate our services along with third-party services into a unified infrastructure configuration. However, it is not always sufficient to have just third-party services, and you need to write your own custom API. For a basic example, we start by implementing our server-side API for the contact form. In the next video, it will allow us to book a calendar slot, but for now, we will just focus on sending email notification. We'll use the Rust programming language to create a unified code base for both server and client-side API. This will help us to focus on business logic first, while allowing low-level optimizations in the future. And we start with defining crates that will be in our workspace. Our initial plan is to have 4 of them: API for the server side, app for static client application, a layer that will be common for all our HTTP servers, and the protocol with our business logic, which will be known for both sides of the application. In our workspace TOML configuration, we can have little generalization with asterisks for the future growth to many microservices. Now, as you remember from the second video, we have a good habit of describing our plans before implementing them in the changelog file before moving forward. Our priority of implementation is and should always be the business logic of our application. So, once our workspace is checked by compiler, we will start working on business protocol crate by pulling the dependencies that we need. Anyhow, crate is responsible for error handling. We obviously need serializing and deserializing frameworks. Chrono will provide us with date and time management. Tokyo gives us asynchronous runtime for network requests. Weirdly named UTO-IPA is used to generate our API documentation. Letter will allow us to send emails, and tracing is an interface for server-side login. Now, let's clear out that some of the dependencies we need are just for server-side rendering, and they should not be included in a client-side builds. And server-side rendering feature set is the default for us. It is nice to think about the business protocol from a high level down to polishing details of its implementation. So, the first structures that we have in mind are obviously request and response of our contact form submission. Both of them are made serializable, and both of them should be present in HTTP documentation schema. But note that deserialization is conditional. Request can be deserialized only by the server, and response can be deserialized only by the client. Such separation is a good start to avoid misusing these structures and give a better reasoning for the future code review, explaining our logic much better. And in general, with Rust development, we are encouraged, if not forced, to use single responsibility principle on every structure that we are introducing. Following it, we are adding one more structure: contact form entry, to which most of the business logic will be applied. Note that this is not the same structure as the contact form HTTP request, despite you may have the temptation to treat it like being the same, but its responsibility is different. It has an isolated optional object of the calendar slot, which is also our point of growth. As our request will use a text string to define such calendar slot in the next videos, we need to do a conversion of such string to our object. Obviously, here we are handling all the error cases. One more conversion function is a conversion from the request structure to our contact form entry structure, and this is the best place to place all error handling. If email or name of our contact message is empty, we will return here an error. And while the next step so far is to send the message, into_lines function will prepare the body of the email. For the demo purposes, we will not use a real email server, and we'll try to use Mailhog, a simple SMTP server for local testing. Now, when we have the definition of the body of the email message, let's define the actual functionality for sending emails. To start, we'd better have a structure that contains our email configuration properties. Clap dependency is used for the properties of the command line arguments. We will have SMTP authorization and host to be defined from our command line interface or from environment variables. Notify function implementation will consist of defining mailbox of the sender, mailbox of the receiver, definition of the message, and the definition of the transport. Note here, a real SMTP server is always under secure protocol, and you should not use build the dangerous function for its transport. But again, things are simplified, and the purpose of this demo is simply to demonstrate a general way of our thinking. Here we have the notification function, so now it's time to test it before moving forward. We will add tests right here in the business protocol crate. We can improve our error handling. The tests that shouldn't be launched on every build or require some additional infrastructure like databases or SMTP server should be marked as ignored. Now I just want to add additional visual confirmation that email was sent successfully. And it looks like it was. Server is one more crate in our workspace, where we'll collect all the common things related to our HTTP servers. Anyhow crate is responsible for error handling. We obviously need serializing and deserializing frameworks. Tokyo gives us asynchronous runtime for network requests. Weirdly named UTO-IPA is used to generate our API documentation. Axon is the main dependency for HTTP server. Tower embeds utilities and middlewares to tune our HTTP server on a low level. And we need to add a few tracing-related crates to be flexible with logs. Prometheus will be needed for monitoring endpoint. This crate will be just one library file that is responsible only for two things. The first responsibility is collecting all needed structures for our future APIs that are actually used in our logic related to HTTP endpoints. What we are trying to achieve here is a prelude style for the future imports. In the target microservices, we will have just one liner that will use all HTTP-related functionality, and this keeps our future server-side endpoints clean and better readable. So, all these lines are declared for public usage. That's why we have a separate crate for this, and in general, it is better to have more crates in your workspace to make Rust compiler cache more efficient on consecutive builds. The second responsibility of this library serves the same goal of code readability, and it will be introducing all kinds of help functions for HTTP server. For our goals, the error responses will be JSON, and we are introducing helper functions to handle all possible server errors in various ways. For example, server should respond to bad input or to internal exceptions with different HTTP statuses. That's what error 400 and error 500 functions here are for. And as you can see their implementation, introducing such functions will make our future code more compact and readable. In addition to helpers, we will have a few more middleware-related functions covered to be simple and compact in a future use. We can have cross-origin resource sharing layer defined, and we can have extended options to adjust our requests and response tracing layer. And we can have one-liner to launch HTTP server easily. Just like many things in this video series explanation, working on server crate can be done only once. And later changes here might be very minor. So note here, we are done at this point with business logic and ensured it's tested. We did that before working on anything related to server or client side. Anyhow, crate is responsible for error handling. Clap is added for the command line interface. UTO-IPA is added to generate our API documentation. Tokyo gives us asynchronous runtime for network requests. And the remaining dependencies are protocol and server. These are crates that are already written, so it's the right time and place to reference them. The goal of this step is setting up main function and plan command line arguments of our future application. And the only command so far will be launching HTTP server in our application. We've already written email config in our protocol, so here it will be included with flatten directive. And we need a network port for listening. That's it with the command line arguments. And main function will be primitive enough. We'll just initialize login and call the function to listen to the port. And under Endpoints folder, we put everything that is related to HTTP in this microservice. That will be application state with our email config and runner of HTTP server with all the routes and middlewares declared here. And here's the trick. When we implement our endpoints, the first thing that we plan is the documentation. Earlier, U2O-IPA package wasn't added accidentally. Describing endpoint as Openapi documentation is actually a priority for us. So, these comments and directives were written ahead of the function body. And as to talk about the body of the endpoint, its structure here becomes dead simple. Get our contact form entry object from the request and return bad request if failed. Then notify admin by email and return server error if it wasn't successful. Okay, there are finally no errors and we can continue. The documentation process continues. Now that the endpoint for the business logic has been described, we need an endpoint to serve the specification for our microservice. This is done by using the Openapi format, formerly known as Swagger. It's an industry standard JSON format used to describe all of our endpoints for external contributors. As you'll see in the upcoming sections, we will need it just as much as the others. Here we have to list all of our endpoints and all of our structures that were annotated as something that can be converted to schema. And we are good to continue. Another essential requirement for our microservices is monitoring. There is an industry standard for cloud monitoring called Prometheus. We'll be adding an additional endpoint to expose metrics in that format. The simplest approach is to include a single integer gauge indicating that the service is live. We won't dive into the details now, but this sets the foundation for future growth, and now you have seen the example of using it. Our server seems to be running and healthy. And the email message seems to be queued successfully. Now, repeating all stages of delivery, we need to Dockerize our new API. So let's write its Docker file, which will probably be the most complex Docker file in this project. It is relatively complicated because we need it to be optimized for consecutive builds, so we will use cargo chef. We will use Alpine distribution, targeting smallest image possible, and we have a workspace setup. All of these little details that add up some complexity. Okay, I should not export gigabytes into the Docker image context. And of course, I should not use typos in the platform name. And we've learned that already in the second video. Let's send the Docker image to a destination server. This is how file system of Terraform plan looks now. Our tactics here is simple. For the start, we will just copy our existing app-demo module as a new module folder. In the input, we will add our email configuration as a new variable. Now it's time to rename all IDs in the new module. And let's map email configuration from Terraform variables into environment variables. In the application layer, we are referencing our new module and figuring out the correct place where a new variable actually should be. That's it. As earlier, Terraform init and Terraform apply commands finally deploy our application. Okay, we are good with our basic server-side API example. In the next video, it will be time to add a persistent storage in a form of PostgreSQL database. So, don't miss the next part.